Welcome to lesson 7.08. At this point we're going to transition into application of the definite integral and antiderivatives. So at this point, if you are in any way not sound in the fundamental theorem of calculus or any of the other conceptual underpinnings we've covered up to this point, it'd be a really good time to go back and review some of that. In addition, we're going to test again on the fundamental theorem of calculus on Tuesday. So again, you'll want to make sure you'll be able to state that clearly and concisely. And once you feel good on that, go ahead and jump in here where we're going to discuss the average value of a function as well as the mean value theorem for definite integrals. All right, so our goal here is to discover the formula for finding the average value of a function over an interval. So go ahead and begin. It starts out easily enough. Work through problems 1 through 4, and then go ahead and press play, and we will finish the discovery and go ahead and actually prove what the formula should be. Okay, so let's start off just by recalling how to find the average of a set of numbers. You're going to add up all of the values and then divide by the total number of values. So in this case, we'd have a sum of 36, and then we divide by 6, and we'd end up with an average of 6. But things get a little more complicated when we want to consider a continuous function, y equals f of x, on a closed interval from a to b. And we'll start off by just thinking, how could we approximate the average y value of the function over that interval? So here's the idea. Similar to how we found the average of these numbers, if we can take a sample of the y values from our function, then we can find the average of that sample, same way we did here. And that will give us an approximation. And then we can think about, based on that approximation, what would we have to do to make our approximation perfectly correct. Okay, so here's what we're going to do. We're going to go ahead and partition our closed interval into n equals subintervals. And the length of each subinterval is just going to be b minus a over n, which we'll denote as delta x. And we're going to pick a number, and we'll call them c sub k, from each of these intervals. And we'll use that number in the interval to find the value of our function. So we'll take f of all the c sub k's. We'll add them together, and then we will divide by n, so that we'll have an approximation for an average value, as I have written right here. Now, let's notice that what we have is 1 over n times this summation. So let's go ahead and represent this summation using sigma notation, and what we'll do is we'll have this 1 over n times this sum. So it'll look something like this. I'll have 1 over n, and then I'm multiplying 1 over n by f of c sub 1 plus f of c sub 2 all the way up to n, so I can write that as the sum from k equals 1 to n of f of c sub k. Okay? Now, thinking about this for a second, we'll notice that this is an approximation. So if we want to get a truly perfect and precise average value of our function, we'd actually need to sample every single point. So instead of a finite sum, we would need an infinite sum. And hopefully that sounds familiar because we've discussed that previously when dealing with the definition of a definite integral. So with that in mind, we'd like to somehow work delta x into our equation here. And luckily, since I have 1 over n, I can actually rewrite 1 over n in terms of delta x here. So I'm going to manipulate this equation as such, where all I've done is multiply on both sides of my equation by 1 over b minus a, so that I have delta x over b minus a is equal to what is now 1 over n. So in my equation here, I can rewrite this 1 over n as delta x over b minus a. Alright, so at this point, take a look at our situation here and notice that if we'd like to take advantage of our definite integral, we're going to need a sum of a product. So we need to multiply our y value by delta x. And so what we'll need to do is think about this sum again and envision it again written out in fully expanded form. And we're going to multiply this whole piece here by delta x over b minus a. So what I can do is I can factor this delta x in and multiply it by each one of my f of c sub k's. And so I can write delta x inside my sum now. And so it'll look like this. And you can see, of course, how this makes sense. If I were to rewrite this sum expanded, I would have all of these products written out, and so I could factor this back out, and I'd have delta x over b minus a times this sum. Now notice, of course, that this is still my approximation that I started with. And so I'm taking a finite number of samples. I have, a certain number of y values that I'm averaging. If I want to find the exact average, I'm going to need an infinite number, right? I need every single y value from my function, and since it's continuous, it has infinitely many of these points, and so I would need infinitely many subintervals, right, where every subinterval was only one point. But we are experienced enough to know that this simply isn't an option. I can't evaluate this sum with infinitely many subintervals. So what are the options that we have? Well, we can use the limit to take the limit of this expression as n approaches infinity. Now notice, when I take the limit of this expression, this part here is exactly the summation that I have within my definition for a definite integral. And 1 over b minus a, this is a constant term because this doesn't change with n. This is already defined as the interval over which the function is continuous. So I can factor this constant out. So let's take a look at that. So notice that all I've done here is factor out this constant from within my limit, and now this limit here is saying, let's go ahead and evaluate this product at every single point from a to b because we have infinitely many subintervals. And so when we do that, delta x turns into dx, infinitely small changes in x, and we are actually just evaluating this at every x value from a to b. In other words, the definition of the definite integral. So we can rewrite this as 1 over b minus a times the integral from a to b of f of x dx. And thanks to the fundamental theorem of calculus, since f is continuous, I know it has an antiderivative, and if I can find it, then I can evaluate this integral with ease, making it very easy now to find the true average value of any continuous function over a closed interval. Let's go ahead and write down this definition exactly now. And this definition is easy enough. If f is integrable on the closed interval from a to b, its average or mean value on that interval is 1 over b minus a times the integral from a to b of f of x dx. So let's go ahead and do a quick example. What we're going to do is actually take a look at what this says graphically very quickly so that you can get a conceptual understanding of why this works, and then we will see that this matches up with the construction here. So go ahead and just quickly sketch this graph. It's fairly simple, 4 minus x squared, so it intersects the x-axis at positive 2 here, and I'm on the interval from 0 to 3. Now, once you've sketched it, what I want you to do is just make your best guess for what the average y value would be. Consider, of course, that there are some negative values here, a few more positive values. So pick that spot, and once you've done so, go ahead and press play. All right, so you probably picked some spot, I don't know, somewhere around here would be my guess. Now, let's go ahead and take a look at what this says to do. It says to take the integral from a to b of f of x dx. And so we can interpret this in terms of the area between the curve and the x-axis. And we know that the area above the x-axis is going to count as positive area, and this here is going to be counted as a negative value, so it will subtract. So now, to understand what the value of this integral is going to be, we can just take this positive area and get rid of the area that will be subtracted away, and we can approximate this with a triangle of base 1 and height 2. So we'll do that, and we'll take this chunk out and we'll look at what's left over. And what's left over in this positive region is going to be the area that corresponds to the value of this definite integral. Okay, so now here's what we want to do. this area here, it's concentrated within the interval from 0 to 2. So let's imagine that we took all this area and let's turn it into a rectangle that goes all the way to 3, so from 0 to 3. So we're going to kind of push this area down and we'll create this rectangle that I will draw, and it will look something like this. So now I have an area here that corresponds to the value of my definite integral, and I can consider quite easily what the dimensions of this rectangle are. First, notice that the base of my rectangle is the full length of the interval, so it'll be b minus a. And the height of my rectangle looks very close to what I predicted the average value of this function would be. So let's just call it the average of my function f. Now, that means that when I find the area, in other words, what I represent this as numerically, will be b minus a times the average value of f, as I've written right here. So I'm going to take this product and multiply it by 1 over b minus a. And so I have 1 over b minus a times b minus a, and therefore I'm left only with what is the average value of my function f, the true height of this rectangle. Okay, so that hopefully helps you believe this even more firmly. And now let's go ahead and actually apply this definition here along with the fundamental theorem of calculus to evaluate our integral to the function 4 minus x squared. Alright, so here I'm simply applying the definition. So I'm going to have 1/3 times the integral from 0 to 3 of 4 minus x squared dx. Go ahead and evaluate this definite integral using the fundamental theorem and multiply by 1/3, and we'll take a look at the solution together. Okay, so here I've evaluated pretty simple antiderivative here, evaluating at 3 and at 0, subtracting the 2, multiplying by 1/3, and I end up with 1. So you'll notice, of course, that this value appears to be the exact height of that rectangle which represented our definite integral, and so when we multiplied by 1 over the width, we ended up with just the value of the height, which we thought was the average, and it indeed is. So this is an incredibly powerful and simple definition. It's really remarkable that something as complex as averaging an infinite number of y values from our function can be so easily computed. Now, one last thing to note is that our function pretty clearly takes on its average value, in this case once along its interval, or along the interval we're considering. And we can prove that thanks to the intermediate value theorem. Since the function is continuous, it will take on all the y values from its left endpoint to its right endpoint. And if we combine this with a little bit of common sense, we can see that no matter what our function, as long as we're able to take the integral of it and compute its average value, that the function will take on that exact average value at least once on that interval. And this is called the mean value theorem for definite integrals. So let's go ahead and write that down. And exactly what that states, here we have it. If f is continuous on the closed interval from a to b, then at some point c in that interval, our function at that value, f of c, will be equal to the average value here, right? So you might want to make a note that this is just the average value that we just discussed. All right, let's go ahead and do a quick example, and then you can get on to the homework. All right, go ahead and find the average value of this function g of x on the interval from 0 to 1. Try it on your own first, maybe do a little bit of research to find the antiderivative here of this function, and then we'll take a look at the solution together. Okay, hopefully that went well. The tricky part of this is actually coming up with the antiderivative here. So if you page back through your derivative rules, you're looking for a function whose derivative is 1 over 1 plus x squared. And this turns out to be the derivative of inverse tangent. So this is going to just boil down to the inverse tangent of x evaluated at 1 and 0, and then subtracted. So we will have the inverse tangent of 1 minus the inverse tangent of 0. And of course, remember, inverse trig functions are read as follows. The angle whose tangent is 1 and the angle whose tangent is 0. And so if you just envision your unit circle, remember, tangent is sine over cosine. In other words, it's the slope of that terminal ray. And so we're thinking about where is the slope going to be 1, and that's going to be at pi over 4. And then where is the slope going to be 0? Well, that's going to be at 0. So I end up with pi over 4 minus 0. And therefore the average value of my function g is pi over 4. If you don't quite believe me, go ahead and take a look at the graph of inverse tangent from 0 to 1, and you should be able to see that this makes sense. All right, at this point, go ahead and move on to the homework for Unit 7.08, and don't forget to take advantage of the long weekend and be ready for the quiz on Tuesday, and in general to move forward using integration.